For problem number 3, we've got a positive charge. It is distributed uniformly around a semicircle of radius 0.2, and the linear charge density is 4 times 10 to the negative 6. So this is our position in question at the center, and before I start choosing symmetric points, instead of choosing the top and the bottom of the semicircle, I can see right off the bat that those are going to cancel out. I'm going to choose symmetric portions of my circle that are symmetric along the semicircle but don't cancel each other out. So I chose a DQ on a piece of the arc, DS, and it's a positive charge. So out of the positive means it's going to go in this direction, and an electric field looks like that. In this scenario, I'm coming again out of the positive piece of charge and in this direction here. And I am going to notice right off the bat that my distance is a constant. No matter where I choose, it's going to be the radius of the circle. I've got a angle here, which is actually changing as I go around the semicircle. So I'm gonna transfer that here. I'm gonna call that d theta because that is changing. And I'm gonna look at the components too. I can see that the y component cancels out. And so I'm focused on this x component here, which is a cosine theta component. Okay. I am doing all the analysis to answer part B, and I am looking at part A and noticing that I've got a pretty easy question here, but it can be complicated to solve if you're thinking about the electric field and you're looking big picture rather than just solving this single part by itself. When we're determining the total charge on a semicircle and they give us the charge distribution, this lambda is the full charge over the full length. And instead of length, I am going to call it full arc length, which is S. Because it's half of a circle, I can use this equation. S is equal to half of a circle pi times the radius. And if it was less than half, then you would take that angle and then multiply it by the radius. This is in your equation sheet, so I showed that to you last class. So then from here, I can solve for Q, which is equal to lambda times S, which again is pi r. And then I can plug in all of my values, which is 4 times 10 to the negative 6, pi 3.14, radius right here of 0.2. And then when you plug that in, you get a Q equal to 2.5 times 10 to the negative 6 coulombs. Okay, so we've solved for the charge, easy peasy. Now we're going to do all the work to solve for the electric field. And I started my diagram up there, so now I'm going to go into my equation. I've got the integral of k dq over r squared. I know that I need to think about the component, the x component cosine theta, so I'm going to go ahead and plug that in. And I also know that this r is given as a capital R, which is the radius of the circle, and that again is a constant. So I'm going to pull out my constants. K over big R squared is equal to the integral of dq cosine theta. Now we are going to first, if I look at dq and I'm looking at cosine, I can't rewrite cosine theta in terms of similar triangles with values that we have because I have an arc here. So I'm going to start with my density equation. I've got density is equal to Q over S, which is also equal to dQ over ds. And so that leaves me with dq is equal to lambda ds. Well, that's also a problem because if I substitute that expression in here, I've now just replaced my dq with a new changing variable, which is my arc length. And I also know that theta is changing. So now I'm going to do a second rewrite. I know that S is equal to theta times R. So if I can substitute ds, which is equal to d theta, a piece of the angle, times the radius, into this expression, then I've rewritten everything in terms of d theta, and my only changing variable is going to be theta. So let's go ahead and do that. I am going to take dq, lambda is given to us, so that's a variable we can use, or a value we can use, and then I'm going to plug in d theta r, or r d theta, into my dq, and that is going to be plugged into this expression. So now I have k over r squared, the integral of lambda r d theta cosine theta. Both of these are constant, so I can pull those out, and in fact the r reduces. So I've got k lambda and the integral of cosine theta d. Now that we've got our variables all in terms of one changing variable, we can think about how my theta is changing. My upper limit, if I start at the top of my charged ring, is going to be 90 degrees, or pi over 2. And then at the bottom, I'm going to get 270 degrees, or 3 pi over 2. And then we are going to integrate cosine, which again, I can't ever remember whether I should make it a negative or positive. In this case, the integral of cosine is positive sign. So I'm going to take my constants and I'm going to substitute, or I'm going to plug in the integral of cosine, which is sine. And then my upper limit is 3 pi over 2. And my bottom limit is pi over 2. So you can find these angles in your equation sheet as well. It's going to be k lambda times -1 minus a positive 1. That gives me negative 2k lambda. And in this scenario, if I plug in all of those values, I end up with negative 3.6 times 10 to the 5th power newtons per coulomb. Now, I know the direction should be to the right. So what I'm going to tell you is solve for the positive. Now, if I were to do it from the lower limit to the upper limit, I would get or from the lower piece of my charge to the upper piece of my charge, I would get a different sign, which is why I think it's valuable to keep the absolute value when you're solving for electric field, and then just find your direction from the diagram, which I already know is going to be to the right. So when I simplify all this down, I get 3.6 times 10 to the 5th newtons per coulomb to the right. Okay. The next thing is to determine the magnitude and direction of an electric force applied by the semicircle on the test charge. Again, because we have our electric field, and we know that that is equal to force over charge, we can solve for force by taking the electric field times that charge, which is just 3.6 times 10 to the 5th times 3.0 times 10 to the -9th. And I got 1.08, which you can round to 1.1 times 10 to the -3 newtons. And again, the direction is to the right, because it is a positive test charge. Okay, again, we did this in part 2. The direction or the motion for this test charge after it has been released. So it's going to experience its strongest force when it's at the origin, and then as it starts moving away from the positively charged semicircle, it's going to decrease in force, which therefore decreases in acceleration, but it's still speeding up because the force is still to the right. So I'm just going to say this in words so I can avoid writing, but the object should move to the right with increasing speed but decreasing acceleration, which again means that the speed is increasing, but the rate in which the speed is increasing is decreasing.